玩那个环视蛋长很厉害。
三大你知道啊？当厉害了，多厉害呢？厉害，不用玩，你先说。
蛮以前，
我不认识名字，
我做后面，
这个哇，真的，
包的
也没有很强，他就是这样，就是稍微晚一点的。
你不是有联营啊？
嗯，
那个有一个挑战不是2024年？
哦，
对
没过
啊，
没打过，
没过。
对，
可是你不是拿那个规章
没有，那个他看错了，不是那个，
啊？
好像13还是14啊，没到后面。
我想拿那个16啊。
哦，老师你有啊？
我要那个
可以加个好友。
啊，对。
哦，那我周二那天我吃坏的故事，然后
哦，OK，
从中午突然就吃坏，
应该是这样子。
就是学习报告。
没有，他就是要充钱嘛，他就是要赚这个。发现它是不是那种累积的？我以为是累积的，有些挑战是累积的。对啊，对啊，我要拿，对啊，我要拿。
太难了，这个16就要拿徽章了。
我也是，
主要是我的号运气不好，我大概7份8份就已经经常排到那个天地拓荒的版，因为这边有牌子，对面牌子过来的，
我从来没有看过的，
没有，我排了好多次。
所以那个基本就是我的牌子。我生这个，那好像是我中学就开始打了，还在我毕业了还在这里。
我也是，我小学开始打，
对啊，对啊，对啊，
小学开始打，
对啊，我的卡牌都是以前玩的，是玩具啊，我还是玩具。
刚52，
你有充钱吗？
没有，那个卡是别人送的，对，
有人帮你充？
没有，就是送的，
怎么充？
他在他的号上买那个月卡，然后直接用身份证付过来，就这样。
因为你不充啊，你天天开啊，也开不到的。还要跟完你了，
我也没有什么卡，
都接到了就这个吧。
就公司高一的。
啊，对，这个就是克我的牌子，这个克我的
没有，我什么都玩起来了，
啊。
就是所有卡都会赢。
比较好奇的是那种可以拉人的，
哪个可以拉小兵？
对吧？然后拉是一堆，然后一堆他们。
那个很难玩的，
对对对对对对对。
愿意。好，知道你。啊，那是我还是应该在上面。哎，知道谁看？去，他想说没钱，说会想中间，那咋办？这期中考复习，期末考后复习就好。万一会吗？ 来考试。
我10号回去。
啊，15那边，25吧，15啊。
越好，那别把那个大个，对吧？有人这你看，大。看后影片。对，在充电。 这一种，公式点。这一个，下一个，牙齿那一群还讨论。哎，你们也哦，这个键定是，要问他们，我是一个技术，面工。哎，这个。这借你们几个？
他在关水啊，应该外接排的很长，再让我们先上来。靠这个 example 很像，
什么方法？给他那个实例，这样子。Also, for example, standard, the cell, that's in that idea. Exactly. 想过这个，想过这个。I think 可能这个有。咱们公司咱们後面咩？佢究竟之後冇揾一隻提升條掣。
好。要求超好要改。有什么想法？然后把语言列出来，3多加到真的在什么都需要外面，就这样的话，四个什么区的那个，照我们是这个宝神奇一点，确实是。所以我就摆的正好就在下面。他们不会这样子的，那意思打在一张桌子。我放在那个以后，什么时候solution的那个标号我就全写掉。OK， 我还有一个法就是你的solution可不可以换题？换什么？换那个题词，叫题什么？叫字体，换成字体，换成什么？或 script solution。哪个 solution？ 就是每一个 solution 可以换它的字体。什么叫每一个 solution？ 把它字体换。是只有 solution part 还是正文里的讲述？是那个 solution 它一个字体。solution 的那个字本，那个字本身可以。因为就是比如说呢，因为如果你 solution 那个名字一样，就感觉来没有差。哦。然后，因为他们一看到那个 solution 的变体，他就他就会被那你觉得我就是那标号的问题呢？如果这样子的话，下面的 x 定上去的那个标号会在哪里？第一，你看你这后面我都每个下面每个它先所有。哦，你是说这个标号是？你不觉得给每题标号会比较舒服？你不能说标回那个选号，那标如果里面有2点，比如说2.2，等于说那个这很麻烦。为难，你不要为难，不是为难，我讲的，这就是为难，不太。这样你要是多少的为难？给我看一下哪一种，你是说哪一种？你是说哪一种example？我叫你不要看哪一种，哪一种？有些就一个嘛，有些会，这个搜发型摸了他们那个蓝海森弄了，其他的更多，什么其他的？不然他看。你要注意哪看看不了。那个是模，我到那。那你其他的空更多，你怎么空呢？一撇毛的，一撇毛的。对啊，一撇毛的就是我。那你那个 page base 不是用来用 page base 那种？干嘛这边我不让他们看不出，你看你看这么多啊，他这个东西看不出，他这个这种说话看不出来，因为把它看出来 S 加里。他不至于吧？是只有这里能把那个写的这个没有问题。特别 this one case， 这边马上不好吗？那不没有太难。就拍照，本来我以为你不想玩呀。哎，我没有看，他把这个 R 给你加出去。也就是 bring the parts 打一下。然后我就问你为什么加进去，因为他告诉他们这个名字怎么。 不好玩吗？你这些答案你这张写它的零是要放过去还是加个 hyperlink？
他没有啊，我在等。
哪里也有啊？他不是讲到哪里啊？我一二三，
过来是吧？这个接头会在改一个是同这个把我们放进总然后那个
停下这一手二。没有，你这写的有些我看都看不清。
对呀，
但是你要求有那么多，我倒是拿你那感觉方便。
对呀。
拜拜。
去哪里？
上水上分。
OK。就只你一个人吧。哪几个？他在哪几个？
就像这种地方。行。像这种地方，你不是就让我把那个 S3提上去？
但是它就是2.27的东西，不是
2.77的叫
2.77不能动。
你不觉得很丑吗？
觉得啊，就是我是说，你又做一个 exercise 出来就，
我都这么干。
我知道，所以我就是说你可以粘在一起。
那你这个地方又
你喜欢去海边玩？
你看你这个地方又缺了个 I
对呀，我说那个 I 的升起来，变升干嘛
？I
因为这个 I，
因为少的是那个 I 啊，对啊。
可是你有没有介绍 ring 那个字？
我怎么就没有介绍 ring？
有介绍 RS 这个字？
有啊，
有没？
不就前面吗？ring without
OK 了
identity。
Okay. Okay. So this is the last lecture. You no need to copy any notes today. 为什么 So you just need to listen, okay, to the story I tell you, okay. And today content will not be in your exam. Okay, no. So you just focus on listen on the story. Okay, I'm gonna tell you. And after that, maybe we can. So what story I'm gonna tell you? So 2 more things I need to tell you about ideals before we finish this course officially finish all the lecture content. So 2 things I'm gonna tell you about maximal ideal and prime ideal. Okay, and then after that, 你们要吃零食吗？ You guys want some snake? 不是 snake snacks. Okay, snacks. Okay. 对，要不要去车拿一下？我的车都。就在你下楼，然后左边的那一排那个车。Okay. Okay, after 2 more definition on ideal, I'll tell you what's the connection. 没有考 Yeah. 你去拿一下回来。And then after that 2 ideal, I'll tell you how we connect to future courses. Okay, like algebraic geometry, abstract algebra 2 from Galois theory, and algebraic topology. Okay, and then after that, I'll tell you maybe some of my thought about you, about your class, and then some of my dream in this university, what we want to achieve in future. and we can take a group photo, and then we can dismiss. Okay. Yeah, if we dismiss earlier, then we dismiss earlier. Dismiss earlier, you want to ask about assignment, we can talk about assignment. Yeah. So why I want to talk about assignment? Because tomorrow, 5 o'clock, we have a badminton, 3 p.m. at badminton hall. So if you want to come, you can come. I already asked all my students to come, every batch, to come and play badminton. 就在学校吧，学校羽球场。So if you want to come and play badminton, make sure you finish your assignment tonight. Okay, make sure you finish before you come. 安排到很妥当。Okay, so let's start. So 2 more things, let's go. So first thing I'm going to tell you is about maximal ideal. Okay, so what's the maximal ideal here? So let's motivate this definition. So let's consider a ring homomorphism. Okay, from R to a field. Okay, so we know that in a field, right, there are really only 2 ideals. What are the ideals for a field? It's just 0 ideal and the unit ideal. Only 2 fields here. Okay, so by correspondence theorems, right, you will have a kernel, okay, or phi that maps to the 0 ideal here. But what is get maps to the whole field here, which is the whole ring? Okay, so from here you can see that there are only 2 ideal that correspond to 2 ideal in the field. Okay, in the field. So if you ask, okay, if you ask, okay, ask the question, what are the ideal? What are the ideal in R that contain curve phi? Okay, so the answer is only curve phi and R. Excellent. Okay, so in this case, we will say that. So we will say that. So here we will say that curve phi is maximal. Okay, so this is the maximal ideal that contains curve phi. Okay, there's nothing in between. Okay, so there's no I such that I is squeezed between curve phi and R. Okay, there's no phi that's squeezed between. Okay, no proper one. Okay, we will say that no proper. Okay, then we'll say that it's maximal. Okay, so let's quickly define it. So a maximal ideal M of a ring is an ideal that such that M is not equals to R and there's no I where I live in between M and R. Okay. Properly. So in other words, what does it mean? It means that if an ideal I contain M, what's the possibility of M? Then this I will be either M or the whole ring. Okay, 2 possibilities. Okay, either the whole ring, either itself. So what's the example you can take? For example, let's go and find a maximal ideal in Z. Can you find a maximal ideal in Z? It's an example of maximal ideal in Z. So what are the ideal in Z? Z is a principal ideal domain. Every ideal is principal. So which ideal is maximal? Which ideal is maximum? Want to guess? 1. 1 is a maximal ideal. So you see 1, what did you get? You get the whole ring, right? But maximal ideal cannot be the whole ring. Okay, so what else? 2. The next thing you can try is 2, right? So 2 is maximal. Okay, 2 is maximal. Yeah, so all the prime are maximal also. All the primes are maximal. Okay. Maybe give an example that's not maximal. 4. Why 4 is not maximal? 4 live inside the ideal generated by 2. Okay, but the ideal generated by 2 is not Z. Okay, so for the ideal generated by 4 is not maximal. Okay, good. So, well, you can prove that actually all the maximal ideal in Z is the principal ideal generated by the prime integer. Okay. You can use division with remainder to prove it. Okay, you can use division with remainder. It's kind of cube proof, but we won't do it. Okay. Okay. All the maximal ideal in Z is generated by prime integer. Okay. Okay, next. So there are few property about maximal ideal here. Okay. So one property is if you have a surjective ring homomorphism here. With kernel I, kernel of 5 I, then the image R prime is a field if and only if I is maximal. Okay, or meaning what? Meaning an ideal I of a ring R is maximal if and only if R mod I is a field. Okay, because this is by first isomorphism theorem, right? So if you take your ring mod out by your kernel, you will get isomorphism with your image, okay, or your codomain, because your image is, because your phi is surjective. Okay, so your image is everything in your codomain. And you also can translate this sentence here, says that if a zero ideal of a ring R is maximal, if only if R is a field. So meaning there's no other ideal that contain the zero ideal other than the whole ring itself. So meaning what? So meaning your ring only have two ideals, zero ideal and a unique ideal. There's no intermediate ideal. Okay. Okay, so let's talk about polynomial ring. Okay, let's talk about polynomial ring. So what can maximal ideal do? Maximal ideal do to the polynomial ring? So here come to a very important concept here. Actually, you didn't realize when you do your assignment, but this is a pretty good result. A polynomial with coefficients in a field is called irreducible okay, irreducible, if it is not constant and if it is not the product of two polynomials. Okay. So such that none of them is a constant. So what do I mean by this? So let me give you an example here. For example, we'll say that x squared plus 1 in zx is not irreducible. Okay, it's not. Sorry, it's irreducible. You cannot reduce anymore. But this polynomial here is reducible. Okay, in C adjoint x. Right. So what's the root of x squared plus 1 here? You can find this root as in minus I. Okay, so you can split it as x minus I times x plus I. Okay, so such that none of them is a constant, okay, in this ring. So it's not irreducible. So one polynomial could be irreducible or reducible depending on what ring you are talking about. Okay, depending on what coefficient you are talking about. This is same as the linear independence. It might be linear independence in Q, I mean not in Q but in R, for example. Okay. And you want to guess? You want to guess what's the maximal ideal in polynomial ring over a field? What are the maximal ideal? Based on the idea you get from Z? Do you want to guess? Yeah. So these are the principal ideal that's generated by the monic irreducible polynomial. By the monic irreducible polynomial. Remember the question you did in what's that question that has a degree 4 in your assignment? It be right. It be question 1B, assignment 7. It is a monic polynomial of degree 4, and it is irreducible over that ring. Okay, if you're gonna split it out, you have coefficient in where? In square root 2, right? Square root 3. Okay, but that's not the ring you consider. Okay or not? Okay, so this is about maximal. Let's go to prime. So what's a prime? So an ideal I is prime if for all A, B in I, so for all the product A, B in I, so if A, B in I, then either A in I or B in I. Okay, so let's give some example. So what are the prime ideals in Z? For example, the ideal generated by 2 is prime in Z. So if you have any product inside this ideal generated by 2, you split it up, both factors should be lived inside Z also. What's not prime here? For example, the ideal generated by 6 is not prime. Why? Because you can write 6 as 2 times 3, but you cannot produce 2 or 3 from 6. Okay, just by multiplication in Z. Okay, for 6 equals to 2 times 3, but 2 and 3 is not in the ideal generated by 6. Okay, so it's not prime. So what's the proposition here? So just now we take a ring mod out by the maximal ideal, we get field, right? So let's say we got a prime ideal here. We want to guess what happened if I mod out my ring by this prime ideal here. Want to guess? Want to guess what we get? Does this prime ideal looks familiar? A, B in I, then A in I or B in I. Just now I give a meme to you right in the class, at the start of the class. AB equals 0 if A equals 0 or B equals 0. So if I kill I, meaning what? All the elements I get sent to 0. So R mod I is an integral domain. Okay, so we can get integral domain by modding out ring using prime ideal. We can get field by modding out ring by a maximal ideal. Okay. So let's do one last thing here. Roller ring. Okay, let R be a ring. Okay, let R be a ring. Then the zero ideal of R is a prime ideal. If and only if R is an integral domain. Okay, so this is similar to the field proposition just now. And lastly, so there's no coincidence why 2 is prime in Z. The ideal generated by 2 is prime in Z. The ideal generated by 2 is also maximal in Z. Because a maximal ideal is always a prime ideal. Okay? A maximal ideal is always a prime ideal. So meaning maximal implies prime. Okay, maximal implies prime. But prime doesn't always imply maximal. Okay. So if you have a maximal ideal in mod out by a maximal ideal, you get field, right? You get field, meaning field is an integral domain. And so you imply that your maximal ideal is always prime. So what's the usefulness of maximal ideal here? Let's talk about some usefulness of maximal ideal. So what's the significance of a maximal ideal? Let's talk about CX, C adjoint X. So why we like C adjoint X? C is an algebraically closed field. Okay, what does it mean by algebraically closed field? Do you know about fundamental theorem of algebra? 啊？高中书，我们高中书好像没有。So what's the fundamental theorem of algebra? It says that what? Every polynomial of degree n can be split into linear factors. So meaning you can find all the roots, okay, in complex coefficient. Okay. So you can write it as the product of linear factor. You know what I mean here? So let's say you have a n plus 1 xn, sorry, an xn, an minus 1, xn minus 1, up to an. You can split this into n root. Okay, product of x minus n. Okay, so right. So once you see this, you can use this fact to see that we can form a bijection. Okay, so what's the bijection here? We can look at all the maximal ideal in C adjoint X. Okay, because C is a field. So we can look at all the maximal ideal here. And this maximal ideal is in one-to-one correspondence or bijective correspondence with points in complex number C. Okay, so what's the maximal ideal here? Actually, this maximal ideal is given by this homomorphism here. C adjoint X to C, right? Because you have a ring homomorphism into a field, then what? Then you can find your maximal ideal using the kernel of this ring homomorphism. Okay, so what's this kernel here? So this is actually a evaluation morphism here. Okay, it's the evaluation morphism. So what's the kernel here? So the kernel of this map is simply what? X minus alpha. Okay, so what's the bijection you need here? What's the bijection you need here? You simply send this polynomial to alpha. Okay. So this create a link between just points with polynomials. Not just polynomials, it's a multiple of polynomials. It's an ideal. So on one side, you have ideal. On the other side, you just have points. Maybe you don't have idea of complex number. A complex number you can draw as a complex plane. Okay, so on every point, alpha here, you can attach a ideal. Hey, you learn calculus too, what did you attach to a point on R2, Rn? Still remember? Vector field. Don't know. Vector field. Forget. Vector field. What do you do for vector field? Vector field is a map from Rn to Rn. So for every point in your space, you attach a vector. But now what do we attach here? We attach an ideal, an algebraic structure. Okay, we attach an ideal on the point. So this is just C adjoint X, right? So actually we can generalize it to C adjoint multiple X. Okay, Xi out to Xn. Okay. So maximal ideal in this ring here. And this is in bijective correspondent to points in Cn also. Okay, in Cn also. Okay. So this theorem is called a Hilbert Nunn-Stellenzer theorem. Okay, so this is the famous theorem before you start algebraic geometry. So what's the kernel here? What's the kernel here looks like? This is, what's the maximal ideal here looks like? It is also supplied by a evaluation homomorphism here. Okay, it's also supplied by a evaluation homomorphism here. So you evaluate this point so that you get complex number. Okay, so meaning what do you need to do? You just need to tell me where you send the xi. And what's the kernel of this map here? So what's the kernel of this map? So this is generated by xi minus ai, okay, for OI. Okay, and this corresponds to a n tuple of points here. Okay, we can do better, we can do better than this. We can do better than this. So if you go and look at our things here, we don't just look at C adjoint the polynomial ring of n variable here. We can look at the quotient, okay, quotient of this polynomial ring. Okay, let's say this idea is generated by R elements, okay, and we look at the maximal ideal again. Okay, look at the maximal ideal again. Maximal ideal of the quotient ring of C adjoint C x1 dot 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 xn by this I here. We can see what. So what then you should guess what's the point we want to consider here? What's in bijective correspondent here? What are the points here? What are the points here? You no longer get the whole C already, but instead what do you get? You get the zeros of Fi, F2 in Cn. So what does it mean by zero of this Fi? You have a polynomial, right? You can solve for the root. So these are the zeros. Okay, you solve for the root. In other words, root of F1 up to Fr. So not F2, it's Fr. So this F is coming from the generator that you quote, the generator of the ideal that you quotient. Then the zeros of these Fi. Actually, you see this example already. Let me show you. You already see this example. So what's the examples here? The example I gave in class is Ct over t squared minus 1. Still remember or not? How many ideals inside here? 4, right? Okay, if you remember, there are 4 ideals inside here. What are the 4 ideals? What are the 4 ideals here? So first ideal is generated by t squared minus 1, the 0 ideals, and then the ideal generated by 1, okay, and then the ideal generated by t minus 1, and also t plus 1. So out of these 4, which one are maximal? T minus 1 and t plus 1. So out of these 4, these 2 are, sorry, let me use another color. These 2 are maximal here. Because why? The first one is 0. The second one is the unit ideal. Okay, so these 2 are maximal, right? But what's the 0 of these 2 polynomials here? 1 minus 0, 0. Minus 1 plus 1, 0. So the zeros are 1. 1 and minus 1. Then these are the 0 for t squared minus 1. Okay, okay. Cool or not? Cool or not? 好玩吗？好玩吗？ Zero of 这个 zero of 那个function, there's a correspondent to an ideal. Okay. 很多个 f 不好举，不好在公共场合下说。这是我们那个 algebraic topology 老师每次讲不要 prove， 我不应该在公共场合 prove 这个。大家要 prove 去办公室 prove。OK， but anyway 下次让我结束掉一些东西。OK。So let me give you more about algebraic topology first. So more algebraic topology. Sorry, algebraic geometry. Let's look at more. So your question assignment 7, question 1C. You still remember what's your question 1C? What's question 1C? You have a map from where to where? R join X, Y, Z to R join T. So what's this map here? You send X to T, Y to T square, Z to T cube. 这个东西你 calculus 3没有学过没 ？2 没有学过没 ？calculus 2没有学过吗？这个东西怎么来的？你 calculus 不然写成这样呢 ？RT equals to T square, T square 跟 T cube 看过吗？这是什么东西 ？Parameterized space curve. So 你可以 you using this parameterization here, you can trace out a space curve here. Okay, you can trace out a space curve here. Okay, so you can treat this x, y, z as 3 coordinates. And what's the kernel here? Maybe I can give you answer lah, but I don't show it to you how to do it. What's the kernel here? The kernel of phi is what? Actually, there are a lot of answers. I mean, few answers to this question. I just show you one answer here. S cubed minus Z and X squared minus 1. Okay, maybe you can pick this 2 choice. There are few choices you can pick, but you need to prove to me. But these are the 2 choices you can pick here. Okay. So what's the geometry significance here? Just now, hey, I think this is the answer you want, right? For this one, I think this example is the answer you want just now. So let's look at C adjoint. So let's look at R quotient of R adjoint X, Y, Z. Quotient out by this ideal here. Okay, then you will find that there's a bijective correspondence between this space curve. Okay, there's a bijective correspondence between this space curve. Yeah. Okay, now. But I mean, I don't know how Tao Xuan taught you, but at least how I taught my class is If you have this parameterization of space curve, right? Where's this function mapping from? This function is actually mapping from R to R3, meaning what? This space curve tells you how this real line sit inside 3D space. Okay, I give you a time, and then you tell me the position in R3. Remember? For example, now it is 5:36. Okay, Adrian is in A1, 2, 0, 4. Right? So I tell you where's the 3D position here. Okay, at this moment of time. Then I can trace out the movement here. But you see, for the space is from R to R3. But when you consider a ring map, it's from R adjoint X, Y, Z to RT. 3-dimensional to 1-dimensional. But if you draw the map out, it's from 1-dimensional to 3-dimensional. So there's kind of a swap of arrow here. When you consider algebraically, then the dimension swap. So there's a induce an opposite homomorphism. This is the structure that we get for algebra. Okay, typically we get. Okay, yeah. For ring map, we have 3-dimension to 1-dimension. But for this, we call it differential geometry. So if we have this differential map, it's going from R to R3. It's differentiable, right? This map, infinitely differentiable. It's a smooth map. Okay, differential geometry. Where is the opposite? Okay, opposite direction here. Okay. I haven't taken 1 hour, so you should have energy yet, right? Let's continue. Okay. Okay, next part. So we talk about algebraic geometry already, right? Let's talk about AA2. What's the connection with AA2? Galois theory. Also, I want to discuss about your assignment question. So your assignment question, question 1B. Yeah, just now we mentioned about question 1B here. Do you still remember what question 1B is? From where to where? QX to Q adjoint square root 2 plus square root 3. Z 是吗？我不知道，忘记了。什么叫 Z？ 看一下。ZQC, sure. ZQC. So let's make it smaller a bit. Okay, maybe I map it to C, right? I make it smaller a bit. I just Q adjoint square root 2 plus square root 3. Enough to make this square root 2 and plus 3 out. Okay, I make it smaller. You make it to C, right? So I make it smaller a bit. Okay. Okay. Well, I mean, surely this is a surjection. Okay, if I don't map to C, then this is a surjection. Fair enough. Surjective, right? This is surjective. Surjective on Q adjoint square root. Because the pre-image of square root 2 plus square root 3 is X. And everything else is just rationalism. Okay. And what's the kernel here? I can also tell you the answer, but you have to show me why is it true in your assignment. So the kernel of this phi is x to the 4 minus nx squared plus 1. Okay. So you should show me that this kernel is this. But basically how you get it, you just take the permutation of root. Okay, later we'll mention about this permutation of root. Okay, so what are you really doing there? Okay, what are you really doing there? So once you have this, right, and you have surjectivity, actually by first isomorphism theorem, what can we deduce? What can we deduce? If I have a first isomorphism theorem, you take your domain, portion out by your kernel, is isomorphic to your core domain. Isomorphic to your codomain. But if you do, but what did we say just now? This is a monic irreducible polynomial. So if you quotient out by ideal general by monic irreducible polynomial, meaning what? You are quotienting out by a maximum ideal. So meaning what? Here is not just a ring. This is a field. This is a field. Field and ring, what's the difference? All the non-zero element is invertible. Okay, so this is actually a field. Okay, so this is actually a field. It actually is a field adjoint square root 2 plus square root 3. Okay, if you do a little hard work, actually this is a field adjoint square root 2 comma square root 3. Okay. You want me to believe me or you want me to show you? Sure. Okay. Okay. So let's show this then. Well, I mean, one direction is easy, right? Which direction is easy? Bottom to up. Okay, bottom to up, right? Because you have square root 2, square root 3, then you add them together, it's just square root 2. Square root 3. But if I give you square root 2 plus square root 3, how you split them up? This is the problem. How to split them up? How do you obtain square root 2 or square root 3 out of this sum here? How? Well, let's do a trick here. So first, I mean, we really have square root 2 plus square root 3, right? Let's just play around with it first. So meaning what? If I square it up, what do I get? 5 plus 2 square root 6. Whoa, actually square root 6 is in here. You extract this square root 6. This would imply that square root 6 live inside the ring. You know why? Because your ring or your field is closed under addition. With Q, right? And also closed under multiplication with Q. Okay, so you can take away 5, you can take away 2. So you can find square root 6 is inside here. Okay, no? Okay. So how does this square root 6 help you? You could take your square root 6, multiply square root 2 plus square root 3. What do you get? 来找一个人算一算。子仙啊，子仙。乘一下。快点乘。square root 6乘 square root 2加 square root 3。乘啊。乘出来是什么？这样 square root 多少？哎，子轩哦，不是，哎，这子轩不是？我没有叫错人哦，子轩，喂，子轩，快点算 square root 多少？square root 1，哎，不可能哎，这个小学生都可以乘给我哎。OK， square root 12加 square root 18。So what is it? 2 square root 3 plus 3 square root 2. Okay. Yeah. So 看得到 C1 吗？有没有看到 C1 这边 ？C1 在哪里 ？Where's your hole? This is also live inside my field, right? So what can you do? You take 2 square root 3 plus 3 times square root 2 minus 2 times square root 2 plus square root 3. Then you can split out your square root 3. Okay, once you split out square root 3, obviously you can split out your square root 2. Okay, no? Okay, yeah. Okay. Right. So why do I want to reduce to this ring here? So let me define one more thing before I show you the magic. So this is called a Galois group. So let's tell you what's called Galois group here. And also this Galois group is where your group come from. Okay, he made this group idea formalized. So if you look at the Galois group, GAL, of this field extension here over Q. In a moment, I'll tell you what these means. Is by definition what? A group. Obviously, a group. So group of what? Group of automorphism. So what's the automorphism? Homomorphism, that is isomorphism, and then map itself to itself. Okay? Map itself to itself. 还是脑笑。我感觉这句英文不错的吧？ Yeah, map it to itself. 对对对。It's a group of automorphism. 谁 between 谁 between Q adjoint square root 2, comma square root 3, fixing Q. Okay, so when we put over Q here, it means that when we consider this map, Q get fixed. Okay, 就是这个就是和那个红瑞，上次是叫红瑞啊，不是红瑞，是另外一个浩瑞呢？浩瑞没有在啊，今天，很浩瑞没有在呢。Yeah， 就是浩瑞提到怎样 map 你的 coefficient field. Okay, usually we just care about fixing one. Okay. Okay, so I give you an example. So let's give you an example. I'll give you some idea. So example, one can check that this Galois group of Q adjoint square root 2 square root 3 over Q is isomorphic to Z mod 2Z cross Z mod 2Z. So what's this generator? So this product group should have two generators here. So what's the two generators here? So this is generated by two automorphism. So it's phi1 that sends square root 2 to minus square root 2 and sends square root 3 to square root 3. And the other one is sending square root 2 to square root 2 and then send square root 3 to minus square root 3. Then you can use this combination to build other automorphism. For example, you can send square root 2 to negative square root 2, square root 3 to negative. You can use composition to build it up. Okay. For example, phi1, phi2, you compose them together. So a very strong result here is by fundamental theorem of Galois theory. So there is a bijection. Okay, bijection between where? Between subgroup of this Galois group. You join square root 2, square root 3, and the intermediate field. Okay, so let me show you what the intermediate field means in a moment. Of Q adjoint square root 2, square root 3. Okay, so what's the intermediate field means? Well, let me show you. So we have a picture of field extension here. Okay, so we extend Q adjoint square root 2 and square root 3 from rational, okay, all the way. But you should imagine that we can right? We don't need to put all of them first. Maybe we can adjoin square root 2 first, or we adjoin square root 3 first. Or there's one more possibility. We can adjoin square root 6 first. Okay. And I mean, with some word, you can see that your final field can be extended from this free field also. Okay, so how to do it? How to do it? So let's say we want to go from rational to Q adjoint square root 2. What's the kernel we need to quotient by? Q adjoint x quotient by x squared plus 2 minus 2. Okay, and then what else? We can go from Q adjoint x quotient by x squared minus 3. And we can take Q adjoint x quotient by x squared minus 6. Okay, and then can we further extend or not? Okay, we can take Q, adjoin square root 2. Okay, adjoin square root 2, adjoin X, and then quotient by what else? X squared minus 3. Okay, to extend to the final field. Okay. Yeah, similarly for the rest. Okay, you can start with this coefficient field, and then you extend. Okay, with the right domain here. I mean, with the right kernel. But on the other side, you can consider what we mentioned about is Galois group. So the first corresponding Galois group here at the bottom is Galois group of Q adjoin square root 2 square root 3 over Q. And then how do you extend it? On the other side, on all the other spot, you could have so at the top you just have a Galois group of Q adjoin square root 2 square root 3 over Q adjoin square root 2 square root 3 again. Okay, so basically you replace the coefficient field using the intermediate field here. Yeah, so let me make it smaller. Okay. But what are these? So one of them I say to you already is Z2 cross Z2. But what's the automorphism that fixes everything? Everything gets sent to X server. You just have identity here. Yeah, you just have identity. If you have an automorphism that fixes everything, that means it is identity. But for the rest, you just fix square root 2. You just fix square root 3. You just fix square root 6. What are the possibility? If you have Q adjoin square root 2, square root 3, you already fix rational number. You already fix square root 2. Where can square root 3 go? Either you go to the positive one or either you go to the negative one. So actually, it is Z2. Okay, so these are actually just Z2. And you can see that there's a subgroup structure here. Okay, Z2 identity, trivial group sit inside Z2, Z2 sit inside Z2 cross Z2. But you can see when you go bottom to up in field extension, your field get bigger. But in the Galois group, they get smaller. Okay, algebra 有很多这种一边变大一边变小的情况，反方向的。Okay, so a very nice structure here. So another thing is about Galois theory is last time we mentioned about the simpleness of A5, right? Okay, so Galois theory says that there's no solution in radical to general polynomial equation of degree 5 and or higher. Why? Because by the same theorem, it tells you that the normal subgroup of the Galois group, okay, the normal subgroup of the Galois group correspond to the intermediate field, okay, correspond to the intermediate field that have the root of this polynomial, right? Root of these polynomial. Okay, so if you don't have normal subgroup, then you won't have the root for a polynomial. Because for A5, I mean for AN where n greater than 5 is simple, so that means there's no normal subgroup. So if your Galois group contains A5, then you cannot split further for A5. Okay, so you don't have normal subgroup to split, meaning you also don't have intermediate field. You don't have intermediate field, meaning what? You don't have the yeah, so if you want to know more, you can go and take A2. 不知道 OK， 再忍一下，再给我4个 slide， 我们就差不多要结束了。OK， 什么？ 你还要 break 咩？我们可以提早 end。如果要回家人可以先回家。Yeah。I think I won't take full 2 hours. So if you want to go back, you can go back. But now I want to finish the stuff first. 还是你们有人有急要上厕所吗？再给我差不多15分钟，应该我就结束了。I will end everything. Okay, if you want to stay, ask about something, you can. If you want to go back to your assignment, also can. Okay. Next course is about algebraic topology. So what's the relation between a group and algebraic topology? For example, you learn about free group on 2 generators, generated by A, B. We can relate to these 2 loops here. Okay, we can relate every generator on your group to a loops. Okay, so here is a base point here. Okay, so what do you mean by loops? So if you do A square, what does it mean? 走2次咯, you work twice on this loop. Okay, if you do AB, meaning you work B first and then you work A. It's still a loop. So when we talk about loop, base point is important. 我要知道起点在哪里，终点在哪里。But it doesn't matter. Once you choose it, then it is what it is. Okay, so let's choose this base point. Okay, and maybe we can consider another group. Okay, generated by A, B square, and BAB inverse. Okay. So can you see the relation between these 2 groups or not? Which one is a subgroup of which? Top is a subgroup of bottom, or bottom is a subgroup of the top. Which one is a subgroup of which? Bottom is a subgroup of the top one, right? Okay, but on this case here, same logic what we did before. Generator sinks to loop. Can you imagine a loop picture for these 3 generators? Can you imagine? A form a loop. B need to work twice only form a loop. And then you can work inverse direction on B and then work A and then work B to get a loop. Can you imagine a picture here? Can you imagine a picture here now? Try it. Yeah. Okay, so let's try my best. So let's do B like this. I do it like this. Okay. So I claim that this is the loop space you're gonna produce. Okay, so if you work A is a loop, work B twice is a loop. So B here is a loop. And then B, A, B inverse. So you work B, you work A, and then is it 要不要画错啊？我想一下。好像 A 画错吧，应该 maybe A 要这样。So let's try again. B inverse A 又不对，我想一下怎么办？有点问题耶。So 对怎么对？Okay, I think it works. Okay, never mind. Actually, 哪一个东西都对其实。Because why do I say it? Why do I say so? Because if you work B inverse, okay, you work A, and then you can work B. Okay, you go from here, base point, you go back. So well, actually there's a phrase here. Actually, this space here is a 2-sheeted covering space for this space. Why 2-sheeted? 2-sheeted means what? Pre-image got 2 points. Okay, so what's the pre-image here? Can you form a map between these two spaces? You can imagine that, for example, these 2 points here will get sent to the base point. Okay. And then you can see that for every point in these 2 loops here correspond to 2 pre-image, 2 points on this thing. So you can say that this map is bigger than the two loop space here. But here, the group that represents this group becomes smaller. Again, opposite. You like alpha. There's an opposite arrow going on both sides. Okay. This space seems bigger, but the corresponding group smaller. It's a subgroup only. Yeah. So actually, this is a loop space of what? Do you know? Can you imagine? 其实我在讨论哪里的 loop space. Where does these two loops happen? Maybe you can imagine you try to rotate the other loops a bit. Okay, let's rotate it like this. Okay, and then on every point on this horizontal loop here, you can do this vertical loop. What is this? What is this? What is this? What is this? This is a donut. This is a donut. This is a donut. 对吗？这是 donut。有两个洞，这边一个洞，然后这里面一个洞。Is a donut. Hollow the donut. Yes. Torus. Yes. Okay, this is what we call S1 cross S1. On S1, you build X1 on top. Okay, hollow, yes, hollow donut, yes. 就是那个 donut 里面是空心哦，然后尖山呢，它反扫那个面粉哦。OK， 没有新的 donut。
这样的话有新的。
有新 you need to attach instead of X1 you attach a D2 you attach a this you attach this right. You attach this then you fill the hollow part and instead of circle you attach this. All right, so this is algebraic topology. Okay, one last thing is this thing here. I mean you must see this before. Every SMUM MAT student must see this before. Even if not MAT, I think you should see also. Because you guys use the same pattern of law. This slide. 看过吗？有没有背到啥那时候？有不是？不是10个咩？10 vector space axiom. Yeah. 10 vector space axiom. 如果你现在看一看啊，感觉好像很多东西看过哎，什么 commutativity 啊 ，associativity 啊，什么 close addition 啊，这个我们叫什么 ？Form a abelian group, right? It's an abelian group. 有 inverse 又有零 identity inverses， 哇，一大堆这些其实就是 group 来的不了。还有一些额外的东西，什么 scalar multiple multiplication. So how do we understand these things? How do we understand this thing? We can understand it as, so okay, let me write to you first. So V is a abelian group, first of all. An abelian group. Second of all, you have a scalar multiplication. Let's say a field or R, 还是你要 R 啊 field 就好了。Field 乘进来 ，how to 乘进来啊 ？I give you a few elements and vector few elements. You give me a vector field. Vector space, sorry, vector field. There's vector space. So 这个是什么东西？给你一个 F， 给你一个 V， 你拿到 FV， 很像 group action 啊。And then if you look at here， 这个 group action 是不是 group action？ Associativity law, associative law, identity law, group action. So 什么是个 vector field? What's a vector field? It is a abelian group with a group action. Sorry, 讲错。A vector space is a abelian group with a group action。that's all， 就这样吧。10个用这2个字就解决了。OK 了。Yeah， 还有distributivity 咯。OK。Yeah， with 一个 extra 的 distributivity 要 build 进来。再说3个东西吧。OK，obedient group action, distributivity, cover the 10 vector space section. Okay, so let's say if your field is your coefficient is not a field, is not coming from field, coming from ring, then we'll call it a modules. Okay, we'll call it module. Maybe I just show you. So I'll show you here, show you the other way. So we can define modules. So module is a vector space of a ring, more general. Okay, maybe our coefficient cannot invert anymore. Okay, cannot invert anymore. And we can define submodules. So submodules, because we have ring, subring, ideal, group, subgroup. Okay, we also can define module, submodule. So what's a submodule? Closed under addition and scalar multiplication. But this is what? It's similar to ideal. So you can prove that the submodules of an R module are the ideal of R. Okay, so ideal is coming from something even more general, modules. And last thing is all modules are representation. So you have seen representation already. What have you seen? You have seen permutation representation. And these are the G modules. Okay, over G. Okay, and then this is what we go, what you can head to representation here. 我们学校还没有这个系耶，没有这个系，没有这个课，没有这么课。OK， 不然先跟你讲我的愿景先，我包一个先来，其中一个先来，either我先走，either我先达到这个愿景。OK， 我们报哪一个？你们也是可以等着看，我也在等着看。OK， 我的愿景是什么呢？OK， 你看一下我以前的成绩单。可以看一下我们成绩单，我想要在这里开的课有哪些？这个是我 first year 了 ，OK，first year 就有2个吧 ，first year only 2 courses on MAT, 1115 and 1116. Our max first year is a combination of calculus and linear algebra， 一起上的，一半。OK， and then second year 比较多数学一个学期拿至少2个。OK， 第一个数学 first sem second sem 就像你跟我一样 second year first sem， 我也是做 analysis 1， 我们做 matrix spaces。So this matrix spaces is actually analogous to the general topology here， 就是那个Eric 叫我在你们前面介绍 general topology， 下个 sem next sem。So if you do general topology, we'll do matrix spaces topology, and I encourage if you could really have to do one pure max course or one MAT course, max course, you have to do general topology. Why? Because it's really similar to MAT2. So if you do 2, it's like buy 2 free 1. So you buy 1, buy 2 free. Buy 1 free 1. Buy 1 free 1. So buy 1 free 1 means what? You study 1, you can take exam for 2. Okay. If you really have to do one pure max, you have to do that. Otherwise, 其他的你也不用想，什么 AA2 你也不用想这个，那些真的是很难。Algebra topology 也是。但是 general topology 就是如果你 if you already take MA2, you should take general topology. Then if you no longer 以后全都不要再碰数学了 ，it's okay， 就是这样，可以的。Yeah, general topology 你一定要拿。Okay. And then we have apply max 2405 about ODE and vectors calculus. And then second sem we have group rings and linear algebra. This is what we learn now. Group rings. And we have PD also, PD Fourier analysis and complex analysis. So which is what you learn next semester. But this is just applied. So this is focused on calculation. So next year, third year. So I have 4 years. So third year, Oh, another one, I learned number theory. So your GE course got that, number theory and crypto. So third year is more interesting here. So on analysis 1, analysis 2, right, I did topology, the back integral. So it's a Lebesgue measure. So the analogous course here is called real analysis. Okay, so if you want to go further in analysis, you should take real analysis. And I did differential geometry. But the differential geometry course here is not really the same as what I did before. My differential geometry is on Riemannian geometry. Okay, yeah, Riemannian geometry. And then I did foundation of maths. So foundation of maths here talk about syntax, logic. So how do you build the logic, everything using syntax? It's like it's kind of very computer science language. Yeah. Syntax and semantic. And then I did field extension and Galois theory. This is equivalent to A2 here. Yeah. Second semester I did complex analysis. I think this should be comparable to your complex analysis next semester. And I did functional analysis. Yeah, functional analysis is not offered to undergrad here at the moment, unless you continue master here. Okay, so they put it into master, but I did it during undergrad. And 3354, there's advanced topic here. So this advanced topic is actually about algebraic geometry. But the algebraic geometry they taught here is different from what I tell you just now. It's a more category theory way to talk about algebraic geometry. It's a scheme way. It's a modern way to talk about algebraic geometry. So a modern way to talk about it is developed by Grothendieck, if you know Grothendieck. And I did algebraic topology in my third year. Algebraic topology in my third year. So it's kind of similar to here. You can do your algebraic topology. And last year, I didn't do much maths. So first part of the course, you can see all its special topics here. What does it mean by special topics here? It's not a proper course. It's a reading course. Okay, so we find a lecturer and then we start this course and then depend on the lecturer what the assessment want to be. Maybe no exam or just assignment or just presentation. Okay, most of the time, even the lecturer don't teach you already. You just read yourself. So that's why I say you guys are quite lucky because there are still lecturer guiding you everything. It's impossible if you go outside. None of the universities like that. So what did I do? I do category theory, commutative algebra, and vector bundles. Okay, and K-theory. Obviously, these cannot be done in undergrad, but it can be done in master. Okay, it could be done in master. There's no courses like this here yet. 没有。没有人教 category theory， 没有人教 commutative algebra， 也没有人教 vector bundle. Okay, so these are very hot topic in algebra research area. And also analysis. Okay, analysis to the end is algebra. Algebra to the end is still algebra. Because it only can get more abstract. That's all. 它只能够更 abstract 上去吧。Ring, group, ring, module, algebra. 越来越 abstract 吧。Okay. Analysis 的尽头是 algebra. Algebra 的尽头是 algebra. Okay. Second sem, we spend more time on thesis, so there's only one course here. And then this course is about hyperbolic geometry. It's a second year course. I just take it so that I can be less pressured and I write thesis. Yeah. Okay. Yeah. So you can see that what I did in my undergrad education is, how to say, quite balanced, I would say. Balanced. I take both analysis and algebra. I'm not go all the way to algebra. I don't go all the way to analysis. I do both. Okay. Yeah, kind of balanced education. So if you can, I hope you can do it also. Okay, yeah. So if possible, we will open these courses in very near future. Okay. Yeah. So okay. 再拉长一点点，我要讲完了。So yeah, maybe some opinion on you guys. Maybe open the line. 还是要关灯比较有动力？开灯了，比较喜欢开灯。Okay, so something I want to tell you guys. So, actually, you guys give a very good impression to me. Actually, 我对你们没有太大的期望，其实为什么你知道吗？因为我打算可能就教你们一个神就没有了，因为反正第二年第一学期啊也做不了什么事情啊，你会就会，不会就不会了，对不对？如果第一年可能还可以训练一下，还可以再走多几年。But you guys it's a little bit different actually， 很不一样，其实跟我教过数学系都不一样。Why is it different? Because you are willing to listen. OK， 这个是很多人没有的一个 ability. There's not much people having this listening ability. OK, you should listen more. Continue to listen. 不管环境怎样 ，no matter how environment treat you badly， 你还是要听。OK， 这是最重要的一点。Only through listening you can learn. You learn by yourself, one day you will stop. 一天你会听。You will meet your limit. You will meet your boundary. 那时候呢，你已经听不进别人讲的话，那你就在 boundary 了咯 ，or less than equal to the boundary。你走不出那个 boundary 的。Research also like this. That's why we have discussion. People like to go to Harvard, like to go to MIT, like to go to Oxford, like to go to Cambridge, because all the great minds are there. So we can discuss. We have breakthrough. Okay, but nowadays it's different because nowadays we have, through internet we can talk already. We don't need to go physically to that space. Yeah, so nowadays it's different. But still, you need to talk. You need to listen to opinion. Yeah. So, well, I'm not sure I will meet you again or not. I'm not sure. I'm really not sure. Yeah. But if you, let's say, if you don't like me, you have to let me know. You have to let me know. Because I don't want to waste time with people that don't want to learn. Why I like you? Because when I taught you, I feel like you are learning. Because I can see from your result, or I see from your progress. Okay, but if you don't like me, you have to tell me. Okay, I don't want to waste time. Yeah. 有这样的，真的有这样的，因为 because how to say people want to have easier life, right? We have easier lecturer for you. Arrange that. So I want to have people that work with the same target. If you want to learn under me, it's good. I think I can bring you to upper level if you are willing to. 我觉得你们班的潜力很无限，我可以把你们带到新的高度，如果你们愿意的话。真的，我没有骗你啊，我真的没有骗你。Yeah， 不止飞起来可能。开过管束，没有啦，开玩笑。But anyway， 就是yeah，so yeah，right， 对 ，OK，yeah，OK，这是我对你们班的印象，可以说是很喜欢，但是不知道有没有机会再遇到，那是另外一回事。OK， 就这样。如果没有遇到就没有遇到哦。什么？我变得很酷了。有遇到我们就再磨一个学期哦。还没有遇到也是可以吃饭，可以的，有时间是可以吃饭的，反正都要吃饭的。我的收入像上面这样高的。OK， 如果这样的话，好不好？我们照一个照相，然后我们就 dismiss， 然后我们 revision 再见。然后我们 revision we can discuss about your assignment 6 7然后还有一些问题做一下 tutorial 题目OK， 来照一个相，我们就 dismiss 要不要全部人来这一项？全部人来这一项？全部人来左边这里。做出牌你不要做出牌，你要站出牌。不要了，站这很乱了。 哎，谁自拍比较强啊？谁手比较长？拿进来。全部人坐去右边那边比较容易拍。
一样啊，一样。哇，这有你了。
啊，你？哦，OK。看得到吗？
看起来我
还是我先帮你调先？要不要我帮你调先？
你要将那个
啊！调了没有？
要光掉，要光掉没？很丑啊！哦，对。
看得到，来放进来。哇，那个 A B 的脚很长去哦。我说这里呗，不要紧，我当旁边。那个顶到，他顶到。他要想他顶高一个人，看到吗？哎，一二三，一二三，一二三。
一二三，一二三，一二三。
看看。
大脑不要
我觉得不能光脚，不能光脚。会抬吗？我觉得不用
抬吗？我觉得抬吗？
不要光脚，
不要放在里面。我就是
光
抬。我讲。
不要光脚。
这样抬吗？
你关上这边。
哦，这样啊，特别得胜。
我对不对？我要跟我的。
有点放眼睛。
那种哈，他想到干嘛来？
不能你1太多，你像0.6。
你有个0.5啊？
什么会跑那？
不用不给钱来的咩？
什么意思？讲钱来，还有位咩？
你呀，你这中间这里不可以咩？
说。
怎么要全部收住哎？
你排哦，你排。
你这样能全部收钱？
你排啊，
钱来
你排啊，排。
我知道排你叫。
怎样排我不知道。
全部人站出来。
你叫，你叫。你帮他一下。你帮他。你帮他一下，你帮他一下。对呀，这样讲好来。出去哪里？
拿出来。
以前好看的。
哦，那个墙壁这样哈。在墙壁这样哈。
没有，你用桌子哦。
啊。
放你的电话卡。
还是我看一下。放不下。
看不到，这样。
没有，我们拍一个全部人在自己的先，然后再拿一个东西顶着拍那个 timer 的。
对，你坐。
你叫全部人出来。
出来，你叫。
来，大家来。早拍完早放学。
They say this is not nice, so we're gonna make a nicer pose here outside here. 来，这个怎样安排？谁来安排？快点安排一下。
这个
快点安排一下，
这全部。
Move here.
没有拉长啊。
光脚。
全部站在那边就可以了。
不要高的在后面，然后中。人家脚拐了。
来 move forward。
高在前面，更高在。
来 move forward。
高往后站。
来往前 move forward。
你看那个脚。
他不伸出来不就行了？那个脚感觉肥了。
来，
我脸也变长了。
看不到，这个后面也看不到啊，所以。
安排一下，帮忙安排一下。来安排一下，后面你看怎样看得到这样多人？
来，
这边有人坐地上。
排呀，我快点排。
地上不能，他不是我讲，有一些人坐地上。
我讲。
这里有地上脚吗？
哪里来的？烧起的。
拿东西
要提
顶。
高一点是吗？
拿这个垫，拿这个垫。
这样顶着。
不要不要，你这里不会平一点吗？拔压，拔压这样子。哇，这个很危险哦，这样子。
可以没？可以吗？
这样吧。
就把这个接上去。